Okay, I'm trying something new. This is a screencast of a Fourier series example. Okay, so this is a continuation of the homework number 1, problem 1 pincast. Okay, so I'm taking the same periodic waveform and I'm applying Matlab to it to calculate the Fourier series coefficients, and from there I can actually calculate also a plot of the Fourier series. Okay, so let me begin by running this and setting some breakpoints. Hang on, let's set a breakpoint right here at C. Okay, so that's fine. Setting a breakpoint there will work. All right, so what I'm doing here is I'm using the symbolic capability of Matlab to calculate an expression for the integral for the Fourier series coefficients, and then I'm going to evaluate that to get numbers out of this. Okay, so let me run to the breakpoint. Okay, and so if I mouse over to C, a yellow box pops up, and you can see it's messy, but it's the integral evaluated. Okay, so this is the same integral that I set up in the pincast, where we integrate 2t e to the minus j n omega naught t. The next variable here, t, tells it the variable of integration, and then I integrate from 0 to 1. The next part is I integrate 2 e to the minus j n omega naught t, with t as the variable of integration from 1 to 2, and finally I integrate minus 2 e to the minus j n omega naught t from 2 to 3. Okay, notice I didn't divide by t. I'm going to do that in another step. I just chose to do it that way. Okay, I defined omega naught in cap t as I did before, and then just because I didn't want to set up another integral, I evaluated this for the DC component by plugging in an n value really close to 0. This is actually numerically kind of a dangerous thing to do, but in this case it works out. Okay, so let's step through this. Okay, and what I want to show you is, first of all, the DC value gives me 1, really close to 1, 0.999. And it's got an imaginary component that's essentially 0, but Matlab gets a little confused by that. So what I'm going to do is I'm going to divide by the period. Okay, so that gives me the 0.25 that I got before in the pincast. And then I'm going to take just the real part to get rid of that imaginary part that happened to be 0. Okay. All right, then I'm going to calculate the first 5 harmonics. All right, so stepping through that, I make n go from 1 to 4, and then I actually the first 4 harmonics, and then I calculate the c's. All right, so I look at that, and this is the Fourier series coefficients in the exponential form. So you should notice there's a real part and an imaginary part for each of these terms. Okay, so to plot things on a computer, the compact trig form works out a little better. So if I step here, I get the c's and the thetas. Okay, so notice the c vector is 1.6944, that's n equal 1. N equal 2 is 0.9762, and the third harmonic is 0.4584. All right. So that gives you the amplitude in front of the complex exponential. Then you can get each of the corresponding phases. Those would be in radians per second. Okay. The next part of this code, you can just use it, but it sets up some time values, and it actually makes a plot of the Fourier series coefficients. Okay, so I wanted to show you something about that. So it's stepping through all these time values. Okay, and for each time value, it calculates the c cosine 2 pi. There shouldn't be a 2 there. N omega naught. Okay. times t plus the phase shift. Okay, so when I step through there, you can look at fs, and you see that's a vector of five terms, one for each of the Fourier series coefficients. Okay, then I add all those together to get the Fourier series. Okay, so when I step one more time, you see the y value. The first y value is calculated to be 0.0732. That corresponds to the first time value. Okay, so we add up the first 5 harmonic terms to get that 0.0732. Okay, from here, there's some technical things about plotting in Matlab that you may or may not know, but you know, if we go ahead and run that to the end, you see we get a nice plot down here of the first 5 harmonic terms. Now that doesn't really look like the original Fourier series at this point, okay? But what I want to do next is go back here and change n to say 50 and rerun this. So when I change it to 50 and recalculate all the terms, you see this is looking more like that Fourier series from the Pencast, okay, where we had the slope of 2t, the constant of 2, and then it shoots down to -2, and then back to 0. I also wanted to point out, you can zoom in and look at the Gibbs effect. Right, you're going to always get this kind of overshoot at a point of discontinuity. And the last thing I want to point out is I plotted the magnitude of the amplitude in front of each of the harmonics. And so you can see how it falls off as a function of frequency, which would give you a measure of the bandwidth of this signal. Okay.